Thanks. I'll begin. Dear Heavenly Father, we thank you for this morning. Again, I thank you for these students. I just pray that you just be with us today, help us to glorify you, Lord, in what we do. And we just thank you, Lord, again for your many blessings to us this day, Lord. In your name I pray. Amen. All right, so I have another example from section 8.6, another rationalizing example for you. Let's see here. So the example is this. We want to integrate the square root of 1 plus e to the x dx. Yeah.
Yesterday, when in the part that you use u equal to 10x over 2,
Yeah.
and then you prove that dx is du over u squared plus 1.
Yeah.
But then in the book, it's actually 2 du.
It says what?
Dx is equal to 2 du over u squared plus 1.
Oh. Oh, no, I missed a factor of 2 yesterday in my Weierstrass substitution. Oh, and of course the earlier section wouldn't have told me about it, as is their custom. Oh my goodness. Yeah, I'll have to put a, thank you. I'll have to put a note in the YouTube videos also. Yeah, I know what it is. I forgot the half in the differentiation. Chain rule. Shame on me. Oh my goodness. Well, I have another example that we might try to do with Weierstrass substitution. Maybe we'll go back through that today then. I should probably do that after I've showed you the numerical integration and such, though. All right, so getting track here. How are we going to do something like this? We've already seen that these rationalizing substitutions can get rid of like square root of x or cube root of x and trade them for a rational function in u. And we also saw that almost correctly that you can you can change a rational function in sine and cosine to a rational function in u with the Weierstrass substitution. What's in the book is correct. What I wrote on the board was slightly wrong. All right, so this one, what we do is we let u equal to the square root of 1 plus e to the x. Now, of course, that will remove the radical, right? Yeah. And then you can do other things like, so u squared is what? U squared is 1 plus e to the x, right? So let's see here, what do we have? Like 2u du is equal to e to the x dx. This gives us dx is equal to what? It's equal to 2 du, rather 2u du. Divided by e to the x, which is what? No need for logs here. E to the x is u squared minus 1, right? I mean, we could do lots of other things. I wouldn't deny you that. But we don't need to, so let's not. If we do this, though, we have what? We have the integral of u, and then dx was what? 2u du, u squared minus 1. All right, so now we're off to the races. This is the integral of 2u squared over u squared minus 1 du, just to clean it up just a bit. Which is a rational function in u, which means we can use our usual bag of tricks from section 8.5, right? Partial fractions. Now, before I can get to partial fractions even, what do I need to do here? This is a improper rational function, right? I got degree 2 upstairs and downstairs. So I got to do something to take care of that. I'm going to use my sneaky adding 0 trick. So this is 2 times u squared minus 1 divided by u squared minus 1. And then what do I have to do to be fair? Right, plus 2. Now the reason I did that, of course, is because I know that if I can create a factor of u squared minus 1 on one of the terms upstairs, then by algebra they cancel out, and it leaves me with what I'm after. Of course, what I'm doing in the red, you could just as well do with long division. If you want to do that, go for it. All right. So there's there's that. Now I need to figure out what's the partial fractions decomposition of 2 over u squared minus 1. So I'll do that next. Let's see here. 2 over u squared minus 1 should be something like a over u minus 1 plus b over u plus 1. Oh, other way around. Wait, I don't know, I can't decide. Anyway, whatever you want to put first. Agree? Because u squared minus 1 factors into u minus 1 times u plus 1. Now what's our next move? Yeah, multiply by the what? Yeah, it's u squared minus 1, so we get 2 is equal to a times u plus 1 plus b times u minus 1. I call this thing Pac-Man. And then we can feed Pac-Man as usual. First thing we should feed the Pac-Man is, how about feed it 1? So that gives us 2 is equal to 2a. How will I solve this equation? I do not know. Oh, yeah. A equals 1. Okay, sorry. You're like, you could give longer pauses for harder things. I know, fine. All right, let's see here. What else should we feed a Pac-Man? Feed it -1. 2 is equal to -2b. Therefore, b is equal to -1. And so there's my partial fractions thought bubble. That gets me from here to here. Integral of twice. Aw, come on. You guys, don't be like section 1. Correct my work. Let's see here. Sorry, I should. Some of them might watch these videos eventually and find out all these things I'm saying about them. Section 1's really great. They understand. They're good people. I have hope for them on the test. Let's see here. Plus, right? Sorry. It will become less funny after I grade the test next Tuesday. 2. So there was a plus, right? I had a minus that shouldn't have had there. Now, so what we have is we've got plus 1 over u minus 1 minus 1 over u plus 1 du. Yay, partial fractions is done. Now we can integrate. And the integration yields for us what? I'm going to put it over here because I did this example earlier today and I know how much room I need, roughly speaking. All right, so this is 2u plus the natural log of the absolute value of u minus 1 minus the natural log of the absolute value of u plus 1 plus a constant. Now we're not done. What do we need to do? Yeah. Well, I could do that. That's true. That's a good point. But before I even get to that, I mean, actually, simplifying this expression before I put exponential back in would make it easier. Interesting. Oh, I won't be so clever, though. I'm going to resist the urge of being clever as instructed and be rather boring. So this is 2. U is equal to the square root of 1 plus e to the x. It's for the purpose of making a point here. Plus the natural log of the absolute value of the square root of 1 plus e to the x minus 1, close the absolute value, minus the natural log of the absolute value of the square root, 1 plus e to the x, close square root, plus 1, close absolute value, plus constant. Okay, so if I gave this as a test question, all right, then in the absence of other instructions, you're done. Okay? I mean, you could make this more simple, but you know, there's a lot of other things going on. So if I want you to like simplify answers, I'll probably include a little comment like, please simplify your answer. But that's a legitimate answer, right? We found an expression in x, which when differentiated will get you back to the integrand. All right? But this can be simplified. How can it be simplified? Right, how about these? I can put these together, right? Let me focus on these two pieces. This is really the same as the natural log of what? Of the square root of 1 plus e to the x minus 1. If you look at it, you don't need the absolute values either, right? Because how about the square root of 1 plus e to the x? What's the smallest it can possibly be? Not even, I mean, it can approach 1, but it doesn't really get there, right? Because e to the x is positive. So 1 plus some positive quantity is never even 1. It gets close to 1, but not even to 1, right? So I don't really need these absolute value bars because this thing is strictly larger than 1. So this is a strictly positive quantity, so I don't really need the absolute value bars. That's one thing. So I'll drop those. But by properties of logs, this is this fraction, right? But square roots and denominators make us angry. So we must rationalize them as we have been taught. So here's the game we play. 1 plus e to the x. Other way around. 1 minus the square root of 1 plus e to the x. 1 minus the square root of 1 plus e to the x. The reason for multiplying by this rather craftily written 1 is simply that it will remove the radical from downstairs. And that leaves us with natural log of what? In the blue. Yeah, upstairs, what do I have? I've got like 1 plus e to the x minus twice the square root of 1 plus e to the x, right? Minus 1. Downstairs, I've just got what? Yeah, I just have e to the x, in fact, because you get 1 plus e to the x minus 1. Oh, man, I did this wrong. Oh, I'm sorry. Why can't I do this? I mean, why shouldn't I do that? I'm sorry. I really should do the other way around. I'm sorry, guys. I wanted to do 1 minus the square root of 1 plus e to the x. Other way around. I'm sorry, I'll get it eventually. 1 plus e to the x minus 1, square root of 1 plus e to the x minus 1. All right, so that makes this plus 1, right? I mean, okay. All right, I think I've fixed it. Square root times square root undoes itself. I get 1 plus e to the x. I get 2 copies of minus the square root of x on the top, and minus 1 times minus 1 gives me plus 1. Downstairs, this times this, so I'm going to write one more step. This is 1 plus e to the x. The cross terms cancel, and you get minus 1. How can we simplify that? What's that? I'm sorry, I just couldn't hear. Oh, yeah, cancel out the 1s. And this is also minus the natural log of e to the x, right? Plus the natural log. And look at the numerator. This actually is what? This is actually the square root of 1 plus e to the x minus 1 quantity squared. So the 1s cancel. I use properties of logs again to pull out minus the log of the denominator, right? And then, let's see here, how does this, great, googly moogly. So how can I simplify that in view of that? So this gives me minus x, right, plus 2 times the natural log of the square root of 1 plus e to the x minus 1. That is a simplified version of what I'm about to circle. So this stuff that I'm circling in red here, right, it is the same as this. I don't think that's particularly obvious, right? So if I wanted you to find your way to what we just found our way to on the test, I would say something like, integrate this function and show that your answer reduces to, well, that's not the answer, right? The total answer is what? It's 2 plus the square root of 1 plus e to the x minus x plus 2 times that natural log plus a constant, right? But if I didn't give you those instructions, where could you stop? At the green line, right? Right there. That's a legitimate answer. It's just, okay, now, so you guys are doing this thing called homework, right? Yeah, you've experienced some of this. This is, by the way, section 8.3, number 3. And the reason I'm talking about this, in part, well, oh man, this is one of your required homework problems. I have deprived you of a certain amount of joy. Can you forgive me? So this is actually a homework problem. And the reason I'm doing this is to show you, I'm trying to explain to you where the answer in the back of the book comes from. The answer in the back of the book has all of this extra jibber jabber to get to this, right? Now, I never said, at least for you guys in the homework, that you're required to get the answer in the back of the book, all right? I do admit there is a certain satisfaction of doing the integration and then finding your way to the answer in the back of the book, right? Certainly there's a satisfaction in that. But I am of the school of thought that you should also get full credit for this answer, right? This is why I will only hire a very intelligent student as a grader for this course. Because my grader needs to understand that what's underlined in green is also a correct answer. Just as correct as the answer in the back of the book, which is simplified. So I don't know. I mean, is the answer in the back of the book a better answer? Sure, yeah. But I can tell that you understand the integration technique if you got to what's underlined in green, so I'd like to give you credit for that. So I wanted to stop and take a minute to talk about that issue, because it's always an issue. Can you get to the answer in the back of the book or not, right? Sometimes you'd rather be asked an even problem so you don't have that on you, if you think about it. Yes, sir?
Well, I noticed, like, when I did integration for the last homework that we just had, I came to a very large answer. It was a guy who I was talking to, and he came up with a shorter answer. He did it a better way.
Mm-hmm.
But I did it, I guess, a longer way.
Mm-hmm.
But the answer looked different than his. But what I asked him was, because I didn't see nothing wrong with what I did, so he said it's pretty much the same answer that I got, because it's condensed it.
Right, so I'm hopeful, cautiously optimistic that the grader will see that. Now, because I expect the grader to see that, he won't look at all of your problems. What he's going to do is he will see, he'll give you there's two components to your score. The one component to the score will be completion. Have you made a legitimate attempt at a certain number of problems? That gives you one number. And then, depending on how much time the grader has, he will randomly select some subset of problems and grade those carefully, each one of those giving you a score between, I told him to give you a score between 1 and 5, depending on the quality of your work. And then we take that, come up with some sort of average number, multiply by the completion score, and that gets you points. So that way you get careful grading of a couple problems, and you also get credit for the totality of your effort. It would be a full-time job to grade everything in here, all the steps, right? You're like, well, you can use electronic homework and then you have instant feedback. Well, yeah, but electronic grading only grades the answer. And it doesn't encourage you to write things down. And that is bad. It's very bad. And yet it is what is so commonplace these days, because we as instructors have become lazy. Sorry, I'm not talking to you guys. Anyway. It would be the easiest thing in the world for me to use electronically graded homework in here. I don't think it's good for you guys, so I don't do it. All right, so any questions about this? Of course, we can come back and do more examples future day, but in the remainder of the time today, I should talk to you about numerical integration. So, and if I play my cards right, I'll get back to this. Dr. Skambordis had advertised this problem to me as being particularly difficult, so I kind of want to try it out with you guys and see what happens. We'll hopefully have time for that. All right, so numerical integration is section, what is it, section 8.7 in your text. And you might ask the question, so why are we doing numerical integration? Oh no, go back. Why are we doing numerical integration? So again, the basic goal here is to look at this look at this definite integral for a given, perhaps for a given function and for a given lower and upper bound. We want to approximate this as best as we can, all right? So before I even tell you how, I think there's questions we should address, which is why. Why do we do this? First reason, it could be that everything I've taught you up to now doesn't work out. Perhaps we can't find an antiderivative, right? It might be difficult, like this, or even impossible to actually find a function, big F, whose derivative is the integrand, right? That can certainly happen. You have some real-world experience with that, right? You've experienced the difficulty of finding big F for functions which look relatively simple. Square root of 9 plus 3x squared. That seems like a simple enough function. Go find its antiderivative, right? It's a pain. But we can do that one. But there are ones out there that you can't do, and some of them are very important to applications. For example, the bell curve, right? This thing. E to the what? E to the minus x squared, something like this. Some constant, you can throw a constant in, I don't know, divide by a or whatever. This function does not have an antiderivative in terms of elementary functions, exponentials, sines, cosines, finite combinations of algebraic expressions. So there doesn't exist a nice antiderivative for that function, and yet it's so important to the study of statistics, right? By the way, it's kind of a very difficult thing to explain. Well, not too difficult, but it's a much harder thing to explain. When is it impossible, right? I've showed you what's possible in here in lots of examples, but when is it impossible to find an antiderivative? And what does that mean, impossible? What is the realm of possibilities? Well, what I mean by realm of possibilities is exponential functions, sine, cosine, algebraic functions, the usual things, right? You have the standard lexicon of functions. How do you know when the antiderivative is outside that world? There actually are specific algorithms. I think it's called Risch's algorithm, which gives a concrete answer to that question for a certain class of functions. So there is actually an answer to the impossible question. But that's, of course, beyond this course. But that is known, and that is part of what Wolfram Alpha and other computer algebra systems are built over, is this algorithm which ascertains when it is or is not possible even to find an antiderivative. Of course, Wolfram Alpha and computer algebra systems know about a whole lexicon of functions that we don't even cover in calculus, right? Like every once in a while, if you've tried out things in here, you might be like, well, the answer is a polylogarithm. And you're like, polylogarithm? What on earth is a polylogarithm? Exactly. Or, oh, it's the hypergeometric function. It's like, well, that's great. But that's not an answer I can use. Okay, so this course partly is about giving you answers you can use, right? And polylogarithms and hypergeometric functions, while being precise, useful things, are beyond this course. So the other thing that could happen, and this is even worse, you might not even have a formula. Consider yourself in the world of experiments. You take some experiments that describe some function. Maybe this integral describes work or power or something else physical, right? You don't even have a formula for the function that you're integrating. You have some data set. Well, if all you have a data set, you certainly can't use fundamental thermocalculus to calculate the area, right? You got numbers. So that's another possibility. Either one of these possibilities drives us to needing another way to calculate that explicitly. And that brings us to the 5 basic numerical approximation techniques that are discussed in section 8.7. Here they are. Here's a picture. I have no love of drawing these pictures, so I decided to leave it up from last class. You can forgive me for being so lazy. So here's the first one. Basically, if I'm trying to find the area under the blue curve, right, I can use rectangles. I can use boxes to approximate the area, right? Here's the left endpoint rule with 6 boxes between A and B. Here's the formula. Sum I equals 0 to 5, f of xi, delta x. Now, the question is, what is xi and what's delta x, right? You should have discussed these things when we defined the Riemann integral last semester. Basically, this is the formulas for the partition. So the 0th one, right, is A. It's coming from the lower bound of the integral. The nth one is B. That's the upper bound of the integral, right? And n is up to you. We can choose n to be, well, for most of these rules, to be anything from 1 to whatever. Turns out for Simpsons Rule, we need an even number of endpoints, even number of points, but one thing at a time. So delta x, we take, it's the length of the integration region, b minus a, divided by the number of the number of approximating regions, n. So that gives me my delta x. To get the jth one, I just take a plus j delta x. This is important because you actually need these to set up the formulas for the left, right, endpoint rules. In other words, all of these rules are basically built from calculating f of x sub I, so it's important to know how to figure out what x sub I is from the endpoints. Let me be less esoteric just for a second here. Sidebar. If I have integral from, say, 17 to 32 of x squared plus sine of x dx, then here I would have a equals 17. I would have b equals to 32. So delta x would be what? (15 over n, right? And so x sub j, or x sub I would be equal to 17 plus I times delta x, which in this case is 17 plus 15 I divided by n. And that runs from I equals 0 all the way out to I equals to n. When you get to I equals to n, you get 17 plus 15, which is again 32. If this is my quote-unquote f of x, what is f of xi? I have to do what? I have to do x sub I squared plus the sine of x sub I. So let's see, that actually is 17 plus 15I over n, quantity squared, plus the sine of 17 plus 15I over n. So what I'm trying to tell you is these formulas look simple enough, and the idea is rather naive, but the actual implementation of these formulas for a specific function can look kind of hairy. All right? Are we good? All right. So you can see here, the left endpoint rule is what? It's going to be certainly it's an under approximation to the real integral, right? We're missing this bit, and that bit, and that bit, and that bit, and these little bits. All right. On the other hand, the right endpoint rule, right, which is based on taking the right endpoint to set the height of the approximating regions, is going to be a what? That's going to be an overestimate, right? This story flips over if I was looking at a decreasing function, right? If I have a decreasing function on the integration region, then the left endpoint rule would be a under approximation, and the right endpoint rule would be an under approximation. And if it was both increasing and decreasing, well, then the story's more complicated. So, the study of how these are approximations to the actual integral, the specific account for how far these are off from the truth, I will talk more about tomorrow. Tomorrow I will talk about the error estimate rules for these things, all right? I'm just talking about the rules today. Okay, so moving on. The next thing would be the midpoint rule. So here I'm defining x bar 1 to be the average. This is my notation. I don't know if he has it in the book or not, but I like this notation. x1 with a bar over it, it's the average of x1 and x2, okay? The average of the first region is x bar 1, the average of the second region, x bar 2, and so forth. You guys get it? So what I've illustrated here is the midpoint rule with 4 approximating regions. Make sense? I mean, there's not much to see. Is that an overestimate or an underestimate? I have no idea. I can't tell from my graph. That's harder to say, right? But with this much we can say, it seems like the likelihood the midpoint rule is closer to the actual integral. It seems like this is going to be closer to the actual integral than one of these guys, right? Okay. And then the next level of sophistication, we're not even using rectangles. We will basically connect the dots. And then what you're left with under it, of course, is trapezoids. How do you figure out the area of a trapezoid? Here's the area of the shaded, this one trapezoid. What you do is you take the average of the heights, right? Like this point right here is what? That's x1, f of x1, right? So f of x1 is the left height. This is x2, f of x2. So that's the right height would be f of x2. Too much. I was going for that, but I think I try that again. Let's see here. Maybe I need to put some like sandpaper on this table or something. I don't know. It's not working. I shouldn't really throw that out. And I mean, this blue one's fine. And who knows what's in that can? I don't really want to reach in and get it. It's kind of dumb. All right. See, I mean, it may be nothing. It may be yogurt. Yeah, who knows? Let's see here. So that's the area, right? Because if you think about if you think about a trapezoid, if you have the average height, right? If you can imagine taking the triangle that's above the average, right? So the average is like right here, right? Something like that. And if you can imagine this, if you could take this little triangle here, right? And you could just cut it off, flip it over, you could glue it below the average, and then you just have one rectangle of the average height and the width, and that would be the area. Do you guys know how to calculate areas of trapezoids? I mean, I personally probably don't remember this, which is my bad. I mean, I can derive it, I guess, but if you've been teaching children how to calculate areas of trapezoids recently, shame on you for not knowing it. But otherwise, I think we probably forget this. But anyway, there's the how to find the area of one trapezoid, like that. And then if you think about adding them together, it's very easy to see where this sneaky uber formula comes from. So this is delta x, right? You have the same width on each trapezoid. You can just factor it out. And then as you add it together, what happens? You got 2 copies of f of x1. You've got 2 copies of f of x2. You got twice of every interior point. And in the sum of these averages, you just have one of the f of a and the f of b, sort of bookending it. And that's where this formula comes from. F of a plus twice the interior points all the way out to f of b, like that. Does that make sense? All right. The next level of sophistication is Simpsons Rule. Now, to derive Simpsons Rule, it would probably take me an hour or a half hour at least of lecture, and I'm not going to do that. So you can read the derivation in the book. So it's interesting. So the idea here is to take and to chop it up into an even number of regions and replace each one of these regions with like a parabolic top. So you fit quadratic polynomials to each little subregion. When you do that and you work it out, you get to this grand glorious formula. It's like this. Now this only makes sense if n is even, I think. Well, I haven't. I don't know. Here's the formula in the book, though, for Simpsons Rule. It's a little bit complicated. It involves both the endpoints and the average points in order to make it all work. So there it is. All right. So on the course website, Simpsons Rule is actually what numerical integrators tend to use. Something like Simpsons Rule is what's behind the scenes in your calculator, from what I understand. I personally haven't taken this course. My brother took a course in graduate numerical analysis, and one of the things they worked out in there was the fact that Simpsons Rule is kind of like the best of all worlds. So all of these different techniques have certain computational complexities, right? In terms of like actually implementing this on a computer. Obviously the left or right endpoint rule, there's really not much trouble implementing that on a computer, right? But on the other hand, the rules start to get more complicated for like Simpsons Rule, right? Now you could imagine, right? You could imagine, oh, maybe if I use cubic, if I fit like a cubic or a quartic on each subinterval and come up with like a generalized Simpsons Rule, maybe that would even get a better approximation, right? And then, of course, as you increase the number of approximation regions, you get closer and closer to the answer, right? But the rub is, in the actual implementation of these, Simpsons Rule is more complicated to implement than that. So yeah, I can calculate left endpoint rule of 60, and I can calculate Simpsons Rule with 60 subintervals. Simpsons Rule will be better, right? But on the other hand, for that given 60, it costs me more computer time to actually execute Simpsons Rule. But on the flip side, Simpsons Rule converges to the actual answer by mathematics more quickly. So Simpsons Rule with 60 is better than the left endpoint rule with 60 in a way that I can describe precisely next time. Not the algorithmics, just the math. Anyway, if you study the algorithmics, apparently it turns out that if you were to try to use things beyond Simpsons Rule like cubic or quartic or other things, you don't gain anything. Simpsons Rule is optimal, weirdly enough. So that's why we use it. I cannot prove that for you in here, and nor have I personally seen the proof of it, but it is something I take on faith. All right. Let's see here. So, you can ask the question, this integral, right? Integral from 3 to 7 of the cube root of 1 plus e to the x dx. Oh, by the way, what I was getting to, I had a link to a website which actually does Simpsons Rule and Trapezoid Rule and draws a picture and gives you a number and shows you how it works if you increase the number or decrease the number of regions, just like an applet, and you can look at it and see it, and it's really pretty. But that link is from 5 years ago. Something bad happened with Java in the last 5 years. And, well, I don't know. I can't get it to work today. I will have to Google. I will find something. I would be shocked if there was not an applet or an app or something which we could just play with that app to understand how the Simpsons and the Trapezoid rule work for a specific example. To my knowledge, there's not a nice way to do Simpsons rule in Mathematica. You have to do Newton-Cotes 3/8 rule or something. You can ask Dr. Wang. I have not enough patience to tell you how to do that in Mathematica. What's that?
He developed a formula where I think you put in partition and stuff.
Yeah, and see, that, in my opinion, is why we shouldn't teach Mathematica or use Mathematica for calculus. If you have to come up with separate code that you have to build by yourself to do something as common and basic as Simpsons Rule. Come on. I'm sorry. Anyway, I digress. This is part of the reason I don't teach Math 133. All right, so sorry, I digress. So this is the cube root of 1 plus e to the x dx. But yeah, Dr. Wang has all the secret formulas, and he spent his whole summer coming up with these things. Good for him. But you know, Dr. Wang is an expert in computer stuff. I mean, you just don't. Dr. Wang is easily worth 20 of our IT people. In a field of battle, symbolically, he alone would stand victorious, with a fine blood mist surrounding him, the heads of all his enemies cleaved cleanly off their bodies. He's that much better than them. You just don't even understand. I'm like, I can't get it to work on the internet. He's like, oh, we just set up a Vultr server, and you can do it on the thing anytime. I'm like, what? So he like makes a fake internet on his computer where he can run app. It's a good thing he's not against the government. All right, so the cube root of 1 plus e to the x dx. You know, the question is, where on earth does this number come from? And I'm relatively certain the answer behind there's a black box there, but it's probably got Simpsons Rule in it. Now, part of the reason we're doing this is we don't want to just black box things. We actually want to see how things go. So Wolfram Alpha is a pretty good, pretty decent tool to do things like this. So what I did was to look at, I want to try to approximate integral from 3 to 7, the cube root of 1 plus e to the x dx. I think there's a chance we could actually find the antiderivative of that using the rationalizing substitutions we looked at today, but I don't really want to either. It seems, I guess it does seem like fun. I will admit that seems like infinitely more fun than this to me. I don't deny it. This is not my bag. But anyway, here it is. The left endpoint rule of order n. So I have to do a couple things, right? I have to figure out what's the formula for the, say, the ith or jth, partition point. So here, 3 plus j delta x. What's delta x? Well, delta x is 4 over n. See, because 7 minus 3 is 4. So here's my x sub j. It's 3 plus 4j over n. Then I have to figure out what is f of that point. Well, that's the cube root of 1 plus e x to the j. So then I feed x sub j into the exponential, and here it is, 1 plus the exponential of 3 plus 4j over n. Then I just do the left endpoint rule, which says sum j equals 0 to n minus 1, the cube root of f of x sub j, which is this. And then I can be lazy. I can factor well, not lazy, I can be smart. I can factor the delta x outside. You have the same width to every box, right? So you can just factor it out. Okay, so here is the left endpoint rule with 100. 0 to 99. Here's delta x, 4 over 100. Here's the cube root of 1 plus the exponential of 3 plus 4j over 100. 22.69. Yeah, let's see here. How far does it what if we just did, say, 10? Left endpoint rule with 10. I got to take my ends and replace them with 10 instead of 100, right? Is that it? I think that's it. Oh, yeah, 10 is wrong. Thank you. Very good. So L10 is like 21.37, like I said. By the way, how would I get the right endpoint rule? Sum j equals 1 to 10 of the same stuff. All right? So it's just a question of shifting, right? I mean, if I basically, you could think about adding one more here like that, right? And if you take this pattern and you just push it over one, you get this. Or if you push the other one the other way, you get that. I mean, they're very closely related, the left and right endpoint rules. Let's see here for this. What do I do? Just j equals. Let's see what the right endpoint rule with order 10 gives us. $24.39. Does that make sense? What is the actual answer approximately? Yeah. Why won't it let me go back? Oh, annoying. Fine. Integrate. 1 plus e to the x cube root from x equals to, what did I have, 3? To x equals to 7. So 22.84, that's in between the left and the right endpoint rule of order 10, right? Which one's an overestimate, which one's an underestimate? R10 is an overestimate. What's this thing look like anyway? Oh. Yeah, I'm sorry, I'm an idiot. Yeah, let me stop. Yeah, you guys are, yeah. I'm not the most observant person sometimes. All right, so, yeah, there it is. Remember my quest to find the laser yesterday. But there it is. I think it makes sense that the left endpoint rule is an underestimate, right? So there is a relation between the left, the right, and the midpoint. I think what happens if we add? No, that's not it. There's a couple of these that are related in some way. I forget exactly. There's a little trick between those. I'll show you that tomorrow. So in the time that remains, which is what? I have 3 minutes. How would you integrate this? Just to remind you, tomorrow I will show you the error estimates for these things, right? These don't really make very good, to specifically calculate one of these, not really an interesting test question in my opinion. I would ask qualitative things about these, like, given the functions increasing, rank these, which is smaller, which is larger, left, endpoint, midpoint. If I give you sufficient geometric data and you understand the pictures, you can answer simple questions about which is an over approximation, which is an under approximation. And tomorrow we'll talk about something that are also quantitative that could be tested about the error in them. But if I haven't assigned you homework problems about those error estimates, it's unlikely I put that on the test. So, all right. So we got what? Integral of what? Dx over 2 plus cosine x. So now tell me the correction to the Weierstrass substitution. What was it? Dx is what?
Dx is 2 du over x squared plus 1.
So I was missing the 2 yesterday? Is that right? Okay, very good. And then what do we have? Sine x and cosine. Oh, I was missing the 2 in the sine x as well?
No. Sine again, cosine was correct.
Oh, okay. So that was what? Was it 2u
Yes.
over u squared plus 1? And this was u squared. Was it 1 minus u squared? 1 minus u squared over u squared plus 1. Okay, there you go. These are the fundamental building blocks for the Weierstrass substitution. So in view of that, this is du. This is 2 du over u squared plus 1 divided by 2 plus 1 minus u squared over u squared plus 1. We clear out the denominator. We get 2 du over 2 times u squared plus 1 minus 1 minus, well, plus 1 minus u squared. How does that simplify? U squared plus 3? Okay. This ain't bad. This is 2/3 inverse tangent of u over 3 plus a constant. I think Dr. Scambordis must have done this without the Weierstrass substitution. What was u? Remember, u was tangent x over 2, right? Yeah, okay. Hey, that's a better example than the one we worked yesterday. Oh, man. Oh, well. So, tomorrow, and what's tomorrow? Thursday. Tomorrow and Friday, we should have time for your homework questions and whatever else. All right? Thanks, everybody.